Okay, so like I said, cylindrical coordinates was familiar as just making the xy plane the polar plane and keeping the z coordinate. So that was we kind of had all those building blocks in place, and it wasn't a big stretch to think about cylindrical coordinates. But spherical coordinates, whole new animal, totally different here. Spherical coordinates, here we go. It's getting good now. Spherical coordinates are three totally new coordinates. We've two of which we've not seen before. One we have. The first is rho. Rho is distance from the origin. So how's that different than r? Rho is a Greek letter. It kind of looks like a P, but it's more like a Greek R. Rho, distance from the origin. How is that different from r that we've seen before? Yeah?
Because for r, if you shifted the polar plane up,
Yep.
it still came off the z-axis, whereas rho would be from the origin, so there's that extra distance.
Right, so r is the distance from the horizontal distance from the z-axis. It's the horizontal distance from the z-axis. Rho is the distance from the origin. So so this would be changing rho, like this. Okay, and we normally don't consider negative rho. Okay, so only consider rho to be positive. Okay, the next one is theta. That's our standard trig angle, or polar, standard trig / polar angle. What is that? Swept counterclockwise from the positive x-axis. I should say angle measure. An angle is an object. Angle measure is a quantity. So our theta is our standard trig polar angle measure. So I can show the theta plane here. So here is theta equals 0. What is the x-axis? And then increasing theta means sweeping counterclockwise from positive x. So we got rho is the distance from the origin. Theta is the standard trig angle. And then the last so here we make so here is theta just a little bit shy of pi over 2. Okay, so it's kind of coming out for, right? It's like from the origin at me. Okay, that's like less than pi over 2. And so the last angle is phi or phi. You say phi, I say phi. Let's call the whole thing off. So what should we call it? Phi or phi? See, even you guys can't agree. All right, we'll go with phi. I'll try to remember. We'll go with phi. All right, so phi. So this is new. This is the angle measure. That's the measure of the angle. Tipped down from the positive z-axis in the plane of theta. So once you've chosen theta, you have this plane theta. Now, phi is going to be the angle in that plane of theta, tipped down from the positive z. Does it make sense? Do you see that? So if theta was pi, back there in the back like that, then phi would tip down in that plane. Whatever the plane of theta is, that's, so you tip down, so this is, it's the angle measure, so it's like this right here. This here is the openness down in the angle, in the plane of the angle theta, the openness tipped down from the positive z-axis. So those three coordinates, distance from the origin. So I guess maybe in terms of the way we think about points, I kind of think of theta first, then phi, then rho. So pick your angle measure first. Let's show that. So here's theta coming around like this. Pick a theta first. So we'll pick it something like, is that like 3 pi over 4? Somewhere around there? 5 pi over 6, something like that in the second quadrant. I'm showing theta in the second quadrant there. Then pick your phi. So this phi equals 0 is the positive z-axis. And then in the theta plane, tip down. So what does phi equals pi over 2 mean? XY plane, right? So it's now we were shooting out horizontally, right? And then greater than pi over 2? Below the XY plane. So then the greatest angle can be is pi. So phi equals 0 is the positive z-axis. Phi equals pi is the negative z-axis. And the angles in between are always in the plane of theta. In the plane of theta, wherever theta is pointing. Okay? So the possible values for phi are 0 less than or equal to phi less than or equal to pi. No negative angles with phi, and nothing greater than pi. So just for practice, plot the point. So I think the standard order is rho phi theta, I think, which is totally backwards from the way that I would think about plotting a point. But I think that's the conventional way that they list ordered triples in spherical coordinates. So let's, can you sketch 3, 7 pi over 6, and 5 pi over 4? Can you find that point in spherical coordinates? Rho phi theta. Can you find and sketch that point in spherical coordinates for practice? 3, 7 pi over 6, 5 pi over 4. Where would that be? See if you can sketch that point.
I thought you said 5 could be greater than 5.
What's that?
I thought you said 5 could be greater than 5.
Oh, what do I mean by that? I meant 2 pi over 3. That's what I was thinking, the right thing, but wrote the wrong thing. So what I mean by that was 2 pi over 3. Sorry. Yes, you're correct. See if you can find that point. All right, next test is next Friday, a week from Friday. 9 days. So I'll have study materials up for you on Friday to start for this weekend. Okay, so what quadrant is it in, first of all? First, second, third, or fourth? Third, 5 pi over 4. It's right about there, like that. Agree? Okay. And then, are we above or below the xy plane? Below the xy plane, we're 2 pi over 3 for phi. So here's 0, right? Tipping down in the direction of theta. 2 pi over 3 is a little bit closer to the xy plane than the z-axis. So maybe something down like that. Let's get a better view here. What is 2 pi over 3? Is it around? It's pretty close to 2, yeah. So that's good. A little bit more. Something like that. And then, what do we do? 3 units in that direction now, determined by those 2 angles, 3 units from the origin. So, right there. So what octant is that in? 1, 2, 3, 4, 5, 6. Is that in the 7th octant? Or 1, 2, 3, 4 is around above the xy plane? Then 5, 6, 7. That's in the 7th octant.
How do we put the octants?
So above the xy plane, 1, 2, 3, 4, just like the quadrants, and then below the xy plane, 5, 6, 7, 8. So 5 is down here in front, 6 is back there underneath and back, 7 is the one we're in. So that's that point that we just plotted. Okay, questions just about the very basics of spherical coordinates? Okay, so then I want you to figure out what sets of points these are. These are all separate problems, so problem A is theta equals 2 pi over 3. Next question, phi equals, oh, these are the, let's see. Oh, that's good, okay. Phi equals 3 pi over 4. Well, let's do 2 pi over 4. Let's do 3 pi over 4. And then rho equals 2. So those are 3 separate questions for each of A, B, and C separately. What set of points would you get for this statement? Theta equals 2 pi over 3, phi equals 3 pi over 4, rho equals 2. So you figure that out. I'll take attendance. No, I'll take attendance at the end. We got longer. Okay, what about theta equals 2 pi over 3? What is that? David? Plane? Almost? You're close? Half plane, right? Half plane, 2 pi over 3 is about close to 2. So that's a plane facing in the second quadrant, something like that. That's pi is 2 pi over 3. Okay, what about phi is 3 pi over 4? Anna, did you get that? So it's phi is 3 pi over 4, so it doesn't relate to this anymore. So when phi is 3 pi over 4, what are all points such that phi is 3 pi over 4? What would that be? 3, 9, 4, something like. Okay, some people are saying it. It's a cone. And which way does the cone open? This opens down because we're below the xy plane. So imagine. Does that kind of look like a cone sweeping around there?
Why does the line make it a cone shape and not the point making it a circular shape?
Because it's all row values.
Okay.
It's every row value along that line.
Okay.
You're right. That if you had a fixed value of rho, then you'd get a circle.
Okay.
But for all values of rho, you get a cone down below the. So let's see if maybe this will help. So do you see that that's making a cone down there? Imagine all points on that line, which is all values of rho. For all values of theta, that will sweep around a cone that opens downward. Okay, and then finally, rho equals 2. You didn't say it's a blue sphere. Just kidding. It's a flashing blue sphere. Right, and so you remember, so I want transparency, not no transparency. There we go. Okay, so later. What's going on? Stop it. All right. So what did we say last time? Why was it called cylindrical coordinates? Why was it called cylindrical coordinates? You remember? What makes a cylinder? What makes a cylinder in cylindrical coordinates? So our, what was it? It was r z theta, right? What makes a cylinder in cylindrical coordinates? Constant r, right? A constant r gives you a cylinder around the z-axis, right? So why is this called spherical coordinates? Almost. Try again. Constant rho, right? A constant rho gives you a sphere. Rho equals 2 is a sphere of radius 2 centered at the origin. That's why it's called spherical coordinates. Very easy to state or represent, express. Very easy to express spheres centered at the origin just by saying rho equals a constant. Okay, so questions on the basics here. Questions on the basics. All right, so let's talk about the relationships between rectangular and spherical coordinates and cylindrical, right? So we're going to kind of bring together. So I'm going to leave up what our spherical coordinates mean. And we're going to turn off that. And so let's do it's good. And we'll zoom in. Okay, that's good. And so we've got this point, which can be expressed as rho phi theta or x, y, z or r z theta. All three coordinate systems can express that point. So let's figure out what's all the relationships between those quantities for a particular point. So how do we do that? So we're going to bring, so what is let's start with the z. What's the z coordinate of that point? What represents the z coordinate of that point? In the graph. How do we get the z coordinate? Whether that's rectangular or cylindrical. Ali, what's the z coordinate? Is this z right here, this distance along this line?
No,
What's that?
that's fine. That's fine.
I heard r and phi. Neither are correct. What's the distance along this line? It's rho. Distance from the origin is rho. So then what would z be for this point? Distance to the xy plane, right? It's the height of the point. Z, it's the same z as it's always been. Okay, and you see that makes a right triangle? I'll try it one more time. Slightly better. That makes a right triangle, right? What was that line I just drew? Does that have a coordinate value? Someone suggested R. Is it R? Yes, it's R. Okay. Where is, do we know any angles in this triangle? Do we know any angles in this triangle? We got the 90, right? Either of these angles known?
The one here, the origin is pretend to be 5 minus 90.
Okay.
90 minus
Therefore, what's this angle? That's phi. How do we know? Because those are what? Alternate. This is phi, right? Angle swept down from positive z-axis. And then that angle up in the top of the triangle is alternate interior to that. Do you see that? So that's also phi. See that? Okay, how do we bring x and y into this? So now I want to bring, so I got r, I got rho, phi, z. I want to bring x, y, and theta into this picture. What do I do? Which is? What's that? Oh, no, that's not right. Try this. That's better. What's that? That's y. What's x? That's x, right? And finally, where's theta? Where's theta in this picture? Right, it's the openness from x to r, right? Oh, that's not that bad. And this is the image. You gotta have these images, right? So this is really important. X, Y, and R, and theta, that's nothing new, right? That triangle that I drew in the XY plane, that's all stuff we've done before. X, Y, so this is the point, what, X, Y, 0? In rectangular coordinates. Okay, we good? Okay, so let's start with how can we write, I want to write R first. What are some different ways I can express R in the other coordinates? So how about this? What about in the xy plane? How do I express or relate R to the stuff in the xy plane? R squared equals? You're thinking this, right? You're just not saying anything, right? Okay, good. Okay, R squared equals x squared plus y squared. Okay, good. And then what about the new triangle that we got here? This vertical triangle with R and Z and rho. I want to relate it to rho. How do I relate R to rho? No, I want to relate it just to rho. What's the hypotenuse of that triangle? Rho is the hypotenuse, right? Rho is the hypotenuse, or right angle. R and Z are right angles. Those are the legs. Rho is the hypotenuse, the length of the hypotenuse. So R is rho sine phi. Because R is opposite phi, right? So related to rectangular coordinates, R squared is x squared plus y squared. Related in spherical coordinates, it's rho sine phi. That's super important. Does everyone see that? So now let's do x, y, and z. What is x? What do we know x to be from before? Yeah, say it loud. R cosine theta. So now we have, how would we write that in spherical coordinates? R is not in spherical coordinates. So I need to write x in spherical coordinates. What would it be? rho sine phi cosine theta. Do you see it? And then what is y? Y is r sine theta, or in spherical coordinates, rho sine phi sine theta. Okay, what about z in spherical coordinates then? So in cylindrical coordinates, it's just z, right? But what is it? So I'll just write it again. Z equals, in spherical coordinates, what is z? It's another leg of this right triangle, so it's rho cosine phi. Yes, these are going to be things you need to memorize, but it should make perfect sense from our picture, right? That where these are all coming from. So I got my x, y, z in spherical coordinates. I got my x, y, z in, cylindrical coordinates. X, y, z in spherical coordinates. I got my r in spherical, my r in rectangular. Any questions so far? All right, so what about my angles? Let's talk about theta first. Theta is expressed how? In terms of the distance coordinates. How's theta expressed in distance coordinates? Arctan of y over x. So now, phi. Let's talk about the inverse. So phi, so we can really write phi in any of the three inverse trig functions. So what are those? Talk about the ranges. Do you remember? So there's arcsine, arccosine, and arctangent. What was the range of arcsine? It always spits out an angle. Do you guys remember this? Arcsine always spits out an angle between? Yep. All possible y coordinates from negative pi over 2 to pi over 2. Arccosine? So now you know all x coordinates, right? All possible x coordinates. What range of angles is that? 0 to pi. And then arctangent, all possible slopes or rates of change would be, again, like this. So, which would be the best candidate for expressing phi? Arcsine, arccosine, or arctangent? Arccosine, because that is the range of phi, right? From 0 to pi. And that's exactly what the range of arccosine is. It comes out 0 to pi. So this is the best choice. So arccosine of what? Arccosine of? Rho. He wants z over rho. Agree? All right. So then how about in Cartesian coordinates? So x, y, and z. Z over what? How do I write rho in x, y, and z? Distance from the origin would be what? In terms of x, y, and z. What's that? Right. It'd be like radius of a sphere, right? Radius of a sphere would be? So there, within that formula is another formula. That rho is the square root of x squared plus y squared plus z squared. Right? And that makes sense in terms of the radius of the sphere, right? Distance from the origin. Square root of x squared plus y squared plus z squared. Okay, if something doesn't make sense, ask. But this should make sense. Yeah, because we're doing arc cosine. It's going to be arc cosine of adjacent over hypotenuse. You see that? So cosine is equal to adjacent over hypotenuse. So arc cosine of adjacent over hypotenuse gives us the angle measure. Okay, ask if I lost you. Yes, please.
How do we come up with square root of x squared plus y squared?
Because it's distance from the origin, right? So what would the distance of a point from the origin be? Right, so you could either think of it as the distance formula or the radius of the sphere. And that's what that is. And so that's rho. And that's also square root of x squared plus y squared plus z squared. Other questions? Okay, so triple integrals and spherical coordinates. They're going to be we're going to have some function of rho, phi, and theta. And if that function is given in rectangular coordinates, you're going to have to change it accordingly, right? Just like you did in cylindrical. You have to change it up so you make sure all your x, y's, and z's are entirely in spherical coordinates. And then dv, right? dv. So is dv, is it d rho, d phi, d theta? What do you think? Phi and theta are angle measures. Is dv going to be base times height, width times length times height? Is this length times width times height? No, these are angle measures. These are not lengths. So it's not. It's definitely not. We've got some work to do here to figure out what dv is. dv is not d rho, d phi, d theta because phi and theta are not lengths. They're not lengths. We're not making. We're kind of making a rectangular cube, but those are not lengths on that prism. So we got to do our homework here. And then we're gonna rho is going to be inside to outside. Phi is going to be starting phi to ending phi. Theta starting theta to ending theta. So the limits we'll do those in examples, but we got to figure out what dv is first. Ready to do that? So let's figure out what dv is. Can I erase the screen? Okay, let's figure out what dv is. So we can write triple integrals in spherical coordinates. So let's bring that down a little bit. See if that works. Okay, so out here at some arbitrary point in spherical coordinates, so I can do this here. What's that? Depends on the problem. There's some problems that I love spherical coordinates. Others that I wouldn't touch spherical coordinates with a 10-foot pole. This is nice. I can change this. Where's my radius of that? Oh. There we go. Okay, so you can still, perfect. Okay, so out at that point, we're going to imagine a little rectangular element. Rectangular element. So see if I can draw this pretty well here. So not bad. That's the best rectangular element I've drawn all day. Okay, so, and that has dimensions. It has a length, a width, and a height. So we got to figure out what those lengths and widths and heights are. according to what? A little change in rho, a little change in theta, a little change in phi. Okay, so a little change in rho is a length dimension. Which dimension is that on my element there? Do you see what d rho would be? Distance out away, right? So it's this dimension here. That's, or this one, or this one. Those are all, do you see that? Those are all d rho. So I'll put it here in the back for space. So that dimension right there is our d rho. Okay, what does, let's see here, let's go with d theta next. So what relates to d theta? Would it be this one right here, exhibit A, or this one right here, exhibit B? Good, exhibit B. So, and we know what d theta is, right? So, or we know what that dimension is. What is that dimension based on d theta? Just like in cylindrical coordinates. R d theta, right? So it depends on how far we are from the z-axis, right? Farther away from the z-axis, that little dimension will be bigger. So the last one relates to what? This here, or this relates to d phi. So what is it? So let me try the. So this is the angle phi, we said, right? So what will it be? So how will we get, using the same logic as that this is r d theta, what will that dimension be? It'll be rho, so now that'll be rho. This length is rho. So that dimension, also this dimension will be rho d phi. And kind of so we got it. So what is our dv is going to be? D rho r d theta rho d phi. Are we done? So this is length times width times height. It's still got the r in there. So if I need to change the r into spherical coordinates, and I've got it. So what is r in spherical coordinates?
Rho sine theta, or rho sine phi.
Which is it?
What?
Rho sine phi. Therefore, we got dv. What is dv? We got rho squared, right? We got a rho from the rho d phi dimension, and then we got a rho from the r, and then sine phi d rho d phi d theta. So that gives the volume. That's our dv. That's like a rectangular prism volume of that little element at the point r rho phi theta. So now we're ready to, we can write triple integrals in spherical coordinates, knowing that that's our dv. So just like before, we've seen before with the r dr d theta, this comes along with dv, but then it links up with our integrand and becomes part of the math of the function that we're integrating. Because it's all multiplication, right? Everything, you take the function you're integrating multiplied by dv, and then this is all multiplied to get a little cube or little rectangular solid volume. So everything's multiplied, so this just links up and multiplies with your function. Okay, any questions on how we derive that? Do you follow it? So this is based on d theta, and that's our r d theta. Then this dimension here is based on a little change in phi, because phi is this dimension here, right?
Which dimension is that?
This one here, or this one, or this one. They're all the same.
Okay.
And so that's based on a little change in phi, and it's going to be the distance out from the origin, rho, times that d phi gives you that dimension. It's very similar to how we got the r d theta. Okay, so let's try a couple easy examples to start. Easier, okay. Spherical is a whole new animal, different beast, so you got to get used to it. Any last chance question on this? Okay, so here's a couple of good examples to start. Light the limits of integration for the bottom half of a sphere centered at the origin with radius 7. And then set up the integral in spherical coordinates to find the volume of the solid that consists of the set of all points between this and the third and fourth octants. See how far you can get on those two. I'll take attendance. Work together. If you're stuck, you don't know what's going on, ask someone. Work together. Okay, first one. Rho goes from. So you say, so that archer. The archer is standing on the origin now, shooting out from the origin, right? So arrow goes from what to what?
0 to 7.
He wants 0 to 7. People are nodding. 0 to 7, that's right, because we're going all the way to the origin, all the way out to the shell of 7. D phi. So bottom half of the sphere. He wants pi halves to pi. D theta. Make sense? First one? Any questions on the first one? Oh, we're actually going to finish. This is awesome. Okay, next one. Oh, I just felt like I went really slow today. That's great. All right, next one. Now I want the volume. All right, so I want the volume of this thing. How do I make a triple integral? Does it give me volume all the time? A triple integral? No, what does it give me? How could you describe what any general triple integral gives? Can you describe it? What's that? Okay, not quite. A little, yeah. Net hypervolume. Difference of hypervolumes. So if you wanted to find the volume of the thing you're integrating over, what would you do? Make the function. Just like double integrals we can trick double integrals into finding area for us by making the function 1. I should go make sure you understand that. I went over that in class one day. It's going to be 1 times. So does this go away then? No, we still need all of dv, right? We still need all of dv. So rho squared sine phi, d rho d phi d theta. Okay, for this thing, oh, I wanted to draw it. What does rho go from? 6 to 9. Is that right?
That row's weird. Oh wait, root 6 to 3.
Yeah, it'll go root 6 to 3. Starting from the inner radius will be root 6 to 3. Phi goes from what? All points between in the third and fourth octants. 0 to pi over 2. And then pi to 2 pi. So we can draw that real fast. You like it? Band shell, right? It's like a band shell.
It's a what shell?
Band shell. Music, right? A music band? Like an outdoor music amphitheater? See it? I kind of had to do it fast. It's like a quarter of a cantaloupe that you took the seeds out.
Yeah.
It's something you put on the
Questions on the limits? Questions on those two examples? So we'll do more spherical stuff next time. Exam next Friday. It's 9 days away.